Hi everyone, welcome to neuroelectrics webinar. My name is Rafał Nowak and I will be your host today. And today we'll be talking about BCI, brain-computer interfaces, and cognitive neuroscience experimentation. And I'm very happy to welcome our guest speakers. We have today with us Dr. Victor Martinez and Dr. Eduardo Santamaria.
Hello.
Good to have you here, guys. So please let me quickly introduce our speakers. Dr. Victor Martinez and Dr. Eduardo Santamaria are professors and research scientists in the field of brain-computer interfaces at the University of Valladolid in Spain. Both are members of the Biomedical Engineering Group and members of the Center of Biomedical Research in Bioengineering, Biomaterials, and Nanomedicine. So this in Spain is called Cyber BBN. Their interdisciplinary research bridges engineering, neuroscience, and implementation of new technology solutions through the analysis of brain activity, e.g. leveraging his expertise in signal processing, artificial intelligence, and large-scale software development. And their main research focus is to advance both scientific knowledge and practical applications of BCI technology. So thank you for joining us today, Victor and Eduardo, and the stage is yours.
Okay, thank you very much, Rafael, for your nice presentation, and thank you to all the participants for being here today. It's really a pleasure for us to be talking here. So as Rafael says, we are going to talk about MEDUSA, which is a software platform that we have developed for the implementation of BCIs and accelerate actually research in this field. No, so we are going to present this software. Well, these are the contents of the presentation. First of all, I'm going to introduce different kinds of BCI experiments that we can implement in our platform and generally in the BCI field. Afterwards, I'm going to talk about the current state of BCI software and why do we need this software. That is why how I'm going to introduce the motivation for MEDUSA. And afterwards, we are going to dive into the main functionalities and key components of this software platform. So there we are going to talk about the different paradigms that we have implemented, the different experiments that you can do. And finally, we are going to, or if the time let us, we are going to perform a live demonstration so you can have a better idea how this software works and what can you do with it. Okay, so first of all, about BCI experiments, well, the possibilities are endless. No, the limit is our imagination. There are a lot of different experiments that we can perform in the BCI field, but I think we can divide them into three categories according to the complexity of the implementation of these experiments. So, for example, this would be the simplest experiment that we can implement, a recording experiment where you are recording the EEG of the patient, and we are going to focus on this biosignal because it's the most used in the BCI field, and you can record the signals while the subject is performing a task, no? And then you can store this data stream into a file to analyze later. So this would be the simplest experiment that we can implement. Depending on the task, this could be a little bit more complex. So, for example, if the subject is reading, or the experiment consists on analyzing the signals while the subject is reading, for example, to see what is going on in the brain while the subject is performing this task, it's going to be very easy. It's going to be direct. But if we are going to analyze, for example, let's say the brain activity while a subject is playing a video game, you are going to have to implement this video game. And perhaps if you are interested in certain events in the video game that you want to analyze in correlation with the neural activity of the subject, you have to synchronize this data with the signal acquisition. But in general terms, this is a pretty straightforward experiment to implement. Afterwards, we have what we call passive brain-computer interfaces. So here we introduce additional stages that are going to increase the complexity of the software development in these cases. Here we are still recording the EEG, but it's going to be processed in real time. So we are going to apply mathematical algorithms to extract meaningful information for an application. And in this case, passive brain-computer interfaces are mainly focused on monitorization, some kind of metric or a state of the subject. We are talking about, for example, sleep monitoring, anesthesia depth monitoring, or, for example, try to calculate in real time the concentration level of a student, which is performing some kind of task. An important thing of these experiments is that there is no active engagement of the subject or the user with the system. So the system is measuring, is calculating, and displaying perhaps information, but the user is not controlling the system. So this is important because it lowers the requirements for real-time processing. The applications are usually simpler. So this is what we call passive brain-computer interfaces. And finally, we have an active brain-computer interface, which is, I think, the more complex experiment or paradigm that we can use in BCI research. In this paradigm, we are measuring the EEG or recording the EEG. We are still processing in real time this signal. We are decoding the signal to guess or to detect the intentions of the user, okay? And and translate them these intentions into application commands. And afterwards, we have an application, okay? So this application is going to execute the command and then give feedback to the user. So we are closing the loop here. So there is an active engagement of the user with the application, and this complicates a little bit things because we have if we want a natural interaction with the system, we have a very strict requirements for signal processing time. The application has to give meaningful feedback to the user. And if we want a natural interaction, this software, this complete system has to work very fast and very efficiently. In this case, we're talking about applications that could be as important as the control of a robotic limb for severely disabled people, neurorehabilitation to improve the cognitive state or some kind of lesion in the brain, or this kind of applications where we have this kind of loops and active engagement of the user with the system. In this kind of systems, in active BCI experiments, we have to implement a lot of things before start our experiment. No, first we have the data acquisition, so we have to implement real-time acquisition of data streams, especially EEG here, but we could also be measuring other biosignals such as ECG or EMG, no, other kind of data too. We have to synchronize all these streams, all these data streams, to have an homogeneous representation of the temporal axis in all the experiment. And then we have to provide real-time visualization. So before starting the experiment, you can check the quality of the signal and see if everything is okay. Then we have to program and develop and implement all the signal processing functions, from basic functions for frequency and spatial filters to more advanced models for active rejection or neural decoding. We are going to talk about this later. And a very important thing is that we have to apply these algorithms in real time. So there are very strict requirements for the time of processing here. And afterwards, we have the application side, which in a lot of cases, it will require high-performance graphical applications, as we will see later. So we will use game engines such as Unity or Unreal to develop these graphical applications. And this poses a challenge also because we have to integrate this with all the previous modules, that the data acquisition and signal processing. And we have to achieve synchronization between all the events that are occurring in the platform, because we probably need to know when the events of the application are occurring to interpret the EEG data and vice versa. No? So these are all the steps, all the implementations that we have to do before starting a BCI experiment. And that's why, and it's very important to use a BCI software, because this software is designed to facilitate BCI experimentation. So we can reduce the development time of these experiments. This software has to have built-in signal acquisition tools for recording, especially EEG, but other data streams as well. Real-time analysis functions. We have to implement all the functions that we need to analyze and decode the EEG in real time. And we'll have ready-to-use BCI experiments, so we can start experimenting with the signals and the paradigms faster. No, the advantages of using a BCI platform, well, there are a lot, because it accelerates the experiment implementation. It reduces the development costs, so you don't have to develop. You can reuse most of the code for your implementation. It improves results, and it enables the participation of non-technical researchers, which I think is very, very important, because traditionally this field is mostly most of the researchers are technical, are engineers, developers, because there is a huge load of software development here. If you want to implement a new experiment, you would have to have this knowledge. A good BCI platform would enable the participation of non-technical researchers, such as clinical researchers, which I think is very, very interesting and brings a different view to the field. No? So these are the main or the most important software available right now. We can talk about signal analysis toolboxes. Probably a lot of you know these toolboxes, such as EEG Lab, Brainstorm, MNE. These are really famous, but they can only be used in the first scenario, in the first case scenario of the experiments, because these analysis toolboxes are designed for offline analysis of EEG signals, other data as well, of course, but we are talking of EEG here. They are designed to be applied offline, so we cannot use these toolboxes in our online experiments, in our real-time experiments, in the second for passive and active BCIs. No. So for this implementation, for these experiments, we will use open source BCI platforms. The most known of them is BCI 2000, perhaps. Also, OpenVive is really important. And there are a lot of projects that are no longer active or no longer maintained, because it's very difficult to maintain this kind of software. The pace of development of the field is really fast. So there are projects that are right now abandoned, such as BF++, XBCI, PyFF, and also there are we have now new software, new platforms that are emerging, such as TimeFlux and Airplane in the last years. So this is an overview of the current platforms. But actually, when we started this project, we identified several limitations, and that these limitations were the motivation for starting the project of MEDUSA. No? So, for example, there is limited compatibility with hardware. In general, for all the platforms, it's difficult to switch between different hardware acquisition equipment for EEG or for other signals. There are the implementation of the previous platforms, especially I'm talking about BCI 2000 and OpenVive, is really complex. They are developed in C++, and they are not user or developer friendly. If you don't know how the software is built, it's very difficult to contribute to it, even if they are open source. They fail to keep up with the latest developments, and I think this is related with the complex implementation. It's really difficult to keep the platform updated with the developments of the field. I'm talking about deep learning or novel paradigms such as code-moderated visual evoked potentials, which is a paradigm that we are going to talk about later. And they lack specific tools to encourage community contributions, and this is, of course, a personal opinion. They are difficult to use, so they pose a challenge for non-technical researchers. The configurations, how to install or compile the software is a bit difficult to use this kind of software. No, and the consequences are clear in this field, in this research field, because these limitations do not foster the development of novel ideas. So researchers end up repeating more or less the same experiments, because we have 3 or 4, 5 paradigms that we end up using, but the researchers focus on databases that have been recorded a long time ago. They process the same database, and it's difficult to advance the field in this way. And I think one of the reasons for that is that the implementation of new experiments and new paradigms is quite difficult, no, because of the reasons that I mentioned previously. These limitations also discourage the participation of non-technical researchers due to the difficulty of use and non-user friendliness. And there is a very important limitation or consequence of these limitations, that is the lack of reproducibility of results. If you can't share your code or your experiment, and this experiment can be used by other researchers, it's very difficult to reproduce results, and that's one thing that it's limiting research in BCI, because it's very difficult to reproduce the results of other researchers, and I think this is important too. So this were the motivations to start our own platform, our own project. In 2018, I think we started. And we are going to talk about all these features in this presentation, but just to sum up a little bit, this software platform is open source. MEDUSA has a broad hardware compatibility through Lab Streaming Layer protocol, which is a protocol that standardized the communication between hardware, equipment, and software. It has a modular, scalable, and flexible design, so we can perform quick updates and keep up with the pace of development of the BCI field. I think we are doing a pretty good job on that way. We use, instead of implementing everything from scratch in C++ or other programming environment, we are using, or we change the focus to the most known environments for signal processing and graphical user interface, which are Python and Unity. So we are reducing a lot of code of other researchers, of other developers, and this is key to reduce the development time of new experiments, of new features on the platform. We have a comprehensive suite of BCI experiments right now. We are going to talk about all or the majority of applications that we have right now in the platform. And we implemented, and I think this is very important too, specific tools to develop and share applications through the app market. So if you're a researcher in the BCI field, you develop an experiment or a BCI paradigm in our platform, you can package it and upload it to the app market. And then other researchers, other users can download the same experiment, the same implementation, and reproduce your results. And I think that's really, really interesting for everybody, especially right now, because we have so many implementations, so many models of different things, and I think this is going to be really useful. Well, just an overview of the 3 key components, or 3 main components of the MEDUSA ecosystem. First, we have MEDUSA kernel, which is an independent Python package that contains all the necessary functions to record and process biosignals, and we are focusing again on EEG. So here we have all the real-time and offline processing of signals that we are going to use in the experiments. Then we have MEDUSA platform, which is a platform that provides real-time visualization and implements function to perform real-time BCI experiments. So the MEDUSA platform is the main component of the platform, because we are going to interact with this component. We are going to receive the signals here. We are going to visualize them. We are going to execute the experiments and the BCI paradigms in this platform. Afterwards, we are going to talk about it more. And of course, we have the website, which in this case and in this project, I think it's quite important, because apart from the documentation and all the things that we have there, there is the key component of the website that is the app market, that it allows the sharing and downloading new BCI experiments. And I think that's a really, really useful feature too of this software ecosystem. So before continuing with the rest of the presentation, I want to say that last year we published a paper with all the information that we are going to talk about here. And if you want to consult it, I think it could help you to understand this framework too. So I'm going to talk about MEDUSA kernel now, which is the Python implementation for all the processing functions and all the analysis functions that we use in the platform. So these functions, we can divide them into two groups. No? First, we have EEG analysis functions, and this includes basic functions from frequency and spatial filters to Fourier transforms or Hilbert transforms. We have implemented local activator metrics, spectral analysis, entropies, complexities, all these kind of metrics that are going to extract meaningful information from the EEG, and that can be applied in online and offline experiments. All these functions are designed to be applied in offline and online experiments. And this is very important too, because it helps us to reproduce the results that we achieve in the online experiments while we are using the BCI system, also when we are analyzing the signals offline. So this is also very useful. We have implemented connectivity and network metrics, especially amplitude and phase connectivity, and also graph theory metrics, pattern recognition models. So we have specific models for EEG decoding based on deep learning, such as EEG Inception, EEG Sim, that have their own publications too. And these models have proven a great accuracy to decode EEG signals. And we also have bindings for scikit-learn, which is a general framework for machine learning for machine learning models. So we can use all the functions in this package too, which is really famous for machine learning. And we also have visualization functions to visualize especially EEG data, but also other kinds of data. And for example, we have here topographic plots and connectivity plots. And afterwards, we have high-level BCI models that use all the previous functions to implement a pipeline that decodes EEG in real time for a specific BCI application. And here we have neurofeedback models, motor imagery, P300 based spellers, and also code-modulated visual evoked potential based spellers. So all these models are used in the BCI paradigms that are implemented afterwards. And now we move on to talk about MEDUSA platform. I here let the word to Victor.
Thanks for taking over, Eduardo. So yeah, I'm Victor. I will be responsible of talking about MEDUSA platform, which is as Eduardo said before, is the graphical user interface for the users to interact with MEDUSA. So, well, the documentation is available at this link here. The platform is the part of MEDUSA that is aimed to provide a graphical user interface to the user, provide real-time monitoring, processing biosignals in real time. And we are talking here about the main functionalities that we have in the platform. So regarding signal acquisition, we support live streaming layer protocol, and this means that we are compatible with any data stream that is being streamed at the local network. And I want to highlight here that we have a multimodal acquisition, and this means that we can record an unlimited number of streams at the same time. Regarding the real-time charts, we have several graphs that we can apply in real time to monitor the EEG and MEEG signals. There are temporal charts, such as single and multi-channel charts, spectral ones, for instance, based on power spectral density, both single and multi-channel, and finally also topoplots, topographic plots that can be based on either band power or connectivity metrics, such as amplitude envelope connectivity. And this is important. We can monitor these signals by applying a preprocessing step before seeing them in our screen. So we have several preprocessing options, such as spatial filters, real time, of course, low pass, high pass, band pass, notch filtering, spatial filtering, re-reference, common average reference, downsampling, and so on and so forth. So when we install the MEDUSA platform, the graphical user interface is completely empty. So the user needs to download different apps to perform the experiments. And we also provide some developer tools in terms of tutorials and also templates for these researchers that wants to develop a customized app for MEDUSA platform. So the platform is, well, this is the graphical user interface. As you can see, it's divided in several modules. Here we have, for instance, in the toolbar, we have the LSL configuration to receive any input signal. Here we have the apps panel. Here the users can install any app from the website, configure any experiment session with these buttons, and also control the life cycle of the app. So start the app, play, pause, stop, and also configure the current app. Here we have the log panel. We are going to see here useful log messages at the platform and also app level. And finally, we have the plots panel. So we can configure here, in this case, we have only 3 plots, but you can configure many plots as you want. And here we have, for instance, a temporal multi-channel plot for the EEG. We have 16 channels here. We have a power spectral density of one specific channel here. And here we have a topographic plot based on band power. So this platform can be downloaded from the website. This is our website, medusabci.com. And well, Eduardo talked before about the reproducibility of the result, and we also encourage the open science. So all this platform code, the kernel code, and other public apps codes are available at GitHub. We have also a community space on Discord to accept several suggestions, bugs in the apps, and so on. And the most important part of our website is the app market. Here we have a collection of built-in apps where users can upload their own apps or download the public apps that are available right now. Of course, these apps, when a user creates an app, he or she can upload it and make it public or private to specific users. Note that when we install the MEDUSA is empty, so user must download one of these apps, and we use a user management system to link the apps that are downloaded by a specific user to show only those apps in the MEDUSA platform. So among the apps that you can download from the website, we have 3 main different blocks. Here, the first one would be the cognitive psychology tests. These are very common psychological tests that can be used to measure some cognitive functions, such as memory, attention, and so on. And the main advantage that we have here in MEDUSA is that we can not only record the biosignal in real time, but also to extract meaningful information from it. So in the digitalized versions of this test, you can extract information such as real or reaction time from the users, but with MEDUSA, you can extract EEG-based metrics such as event-related potentials, which can be very useful here. Secondly, we have the state-of-the-art BCI paradigms. There are common paradigms that are aimed to control different BCIs, such as these spellers, or to perform some endogenous control signals, neurorehabilitation, cognitive training, and so on. And thirdly, we have, well, another block, which is other apps. So here we can have the recording app just to record an experiment, or for instance, some apps aimed at recording several visual ocular artifacts to train different artifact rejection models. So let's focus on the first type, which is the built-in cognitive psychology test. First, we have the Stroop task. Maybe you already know that the Stroop effect is a delay in reaction time that users suffer between congruent and incongruent stimuli. And this test is usually used for measure selective attention, cognitive flexibility, and also processing speed. So the task is as follows. Well, this is in Spanish, but a color word is presented to the users, which is colored with another different color. So users must click on the button that represents the color of the word, but ignoring the meaning of the word, right? So in this case, we have azul, which means blue, but it's colored in red, so the users must click on the red button. We have also the Corsi block tapping test. This test is useful to measure visuospatial short-term working memory. The task of the user is to mimic a sequence of flashes after it is displayed. So for instance, you can see here that we have this sequence of flashes. The user must remember it and then click on the blocks. In this case, the user has made a mistake. Well, for healthy subjects here, we could expect an average of 5 to 6 expands. We have also the digit span test, which is very similar to the previous one, but in this case, we don't have 2D visual spatial information, only numbers. So we are measuring the short-term working memory, and the objective of the user is to mimic a sequence, and in this case of numbers, after it is displayed. So the user must remember this sequence and input them via keyboard or mouse. Here, we could expect from a healthy subject an average of 5 to 9 spans. We have also the go or no-go task. In this case, we are measuring response inhibition, which is the capacity not to respond to an event. So the user must press the space bar whenever the go stimulus is presented. In this case, the go stimulus is the green coin that we have here, and inhibit in case of a no-go stimulus, which can be the red coin or also the cross. So whenever the green coin appears, the user clicks to the spacebar. Here we can not only record or to measure reaction time, but also event-related potentials or even error-related potentials when they are using and performing the experiment. And finally, we have the dual MBAC test. In this case, this is aimed at measuring the working memory of the subjects. And the task is as follows. The users must indicate whenever a stimulus matches the stimulus that is presented n times before. For instance, if we have n equal to 1, the users would click the spacebar, in this case, if the previous stimulus is exactly the same to the current stimulus. When n equals to 2 or n equals to 3, things become very significantly more difficult for users. So let's move to the built-in BCI paradigms that are currently available to everyone in the app market. Well, after or before explaining this, as you may know, thinking is not directly reflected in the EEG due to its complexity and also due to the low spatial resolution of the signal. So for non-invasive BCIs, we need to rely on control signals that are strategies that can provoke a change in the EEG that is correlated with the user's intentions. So we have two main types of control signals, self-regulated and natural responses. The first ones, or endogenous signals, are self-regulated EEG changes. So the users must learn to control them to generate a specific brain activity over different locations and different frequencies. And an example here would be their sensory motor rhythms, or SMR. In the other part, we have here the natural responses or exogenous signals. These are natural responses of our brains to different stimuli. This stimuli can be visual, can be sensor, tactile, or auditory. And in this case, we have examples such as steady-state visual evoked potentials or code-modulated visual evoked potentials, CVEP, that are responses to visual flashes following pseudo-random sequences. And we have some control signals that are a mix between the two, endogenous and exogenous, because they can have endogenous and exogenous components in their generation. And for instance, here we have the P300 evoked potentials. So one of the classical control signals in BCI in general are these, the latter, the P300 evoked potentials. They are positive deflections in the EEG in response to different infrequent stimuli, approximately 300 milliseconds after the onset of the stimuli at centroparietal skull position, and they are generated using Oswald paradigm. So you can see here that the target stimuli is deviating from the non-target stimuli as the number of infrequent stimuli increases, right? So this can be generated using an Oswald paradigm, which is based on presenting a rare target stimulus with the user, in which the user must attend to masked amount another background more frequent stimuli. In this case, the target stimuli would be the face of Einstein. So whenever the user receives this stimuli, no P300 will be provoked here, but whenever the user sees the Einstein's face, because this is the target stimuli, P300 will be elicited here. So we can extend this Oswald paradigm to provide a real-time communication using P300 evoked potentials in BCIs, for instance, using the row call paradigm or RCP. Here, as you can see, the rows and the columns are constantly flashing randomly. So only one row and one column is flashed at a time, and the user must pay attention to the command that he wants to select. For instance, if the user is paying attention to the O, only this row and this column will elicit the P300 potential. So detecting what is the most likely row to be selected and the most likely column, we can determine what is the command that the user is looking at in real time. So, well, of course, MEDUSA already provides a built-in app for these RCP spellers. But RCP spellers are a classical implementation to provide BCI communication, but they are quite slow. So in MEDUSA, we have also several apps using the code-modulated visual evoked potentials, or CVEP, which is a cutting-edge paradigm to reach high performance with a very brief calibration. So these CVEPs are visual evoked potentials that are generated as a response to a pseudo-random flickering code. Code is shown at a fixed rate, normally 60 Hertz or 120 Hertz in case of, well, it depends on the monitor refresh rate, and they are mainly generated over the occipital cortex. So let's see that we have here this pseudo-random binary sequence. So we have zeros and ones that are encoded with flashes, black and white flashes. So this sequence would generate a specific response over the visual cortex, of the occipital cortex, right? So the most surprising thing here is that this response is unique to this sequence of flashes, and the response could vary if we use another pseudo-random sequence. So we can take advantage of this phenomenon to create another communication speller. In this case, we are talking about circular shifting paradigm, which is one of the most recent approaches in non-invasive BCIs. So here we are going to encode the different commands with shifted versions of the same code. And here the code must fulfill only one requirement, that is that the code must have a flat autocorrelation profile, for instance, M sequences. So this is the flat autocorrelation profile. This could be the M sequence. And we are encoding different commands with the same sequence, but shifted temporally, right? So we first record what is the BEP in response to the original code, this one, to use that as a template. And after that, in an online page, so when the user is looking at any given command, we compare the response when the user is looking at this command to the template and the shifted templates according to the lags of the different commands. So we select the command that yields the highest correlation here. So in MEDUSA, we have several implementations of these CVEPs with small differences. Here, Eduardo is controlling a circular shifting paradigm with the Novia system from neuroelectrics. This speller is quite more complex, and it also have an early stopping algorithm. So as you can see, the trial duration is not the same for each selection, right? So note that previously to this, Eduardo has undergone a calibration of 1.5 minutes. In the market, we have freely available 2 apps related to CVEPs. One is the CVEP speller, which has a version with binary sequences, black and white. And we have also the PRV CVEP speller, which is, well, you can use another M sequence with higher bases. So you can encode the different commands with different shades of gray or different colors. And it was demonstrated that this reduces the user visual fatigue. Here we have another implementation. In the market, we also provide this app, which is a multiplayer video game using CVEP. This is the well-known Connect 4 video game. So this game challenges the users to compete and to place vertically, horizontally, or diagonally 4 coins of the same color. So here, Eduardo and I, we are taking turns to place the red and the yellow coins. In MEDUSA, we also have apps that are related to endogenous signals, not only exogenous ones. For instance, we have apps related to the sensory motor rhythms, or SMR. They are self-generated neural oscillations that are generated before, during, and after movement, execution, or even movement imagination over the sensory motor cortices. This usually involves a desynchronization at alpha frequencies, followed by synchronization at beta frequencies. Normally, this is known as ERS, event-related synchronization, and ERD, event-related desynchronization. So, of course, these signals are generated in contralateral hemispheres. So if you are imagining the movement of your left hand, this would elicit brain activity over the right hemisphere, for instance, electrode C4. And if you are imagining the right hand movement, so that would elicit an ERD and ERS over the left hemisphere, for instance, 3-3. So we have here some graphs related to this event-related synchronization and desynchronization. Here we have a toy implementation of these SMRs. Here we have only 2 degrees of freedom, imaginations of the right hand and the left hand. And as you can see, the cursor in 2D is moving to the right or to the left, and also the ball is being colored. This is also available at the app market right now. However, these SMR signals only offer us a control of 2 to 4 degrees of freedom, 2 to 4 commands, typically 2, left and right. So they are not usually the most appropriate option for BCI for communication and control. Nevertheless, the effort to learn to control these signals has been demonstrated to induce neuroplasticity, so they can be used for clinical purposes, such as neurorehabilitation or cognitive training. So here we present an implementation within MEDUSA. This is a private app aimed at facilitating neurorehabilitation for stroke survivors that has an spastic hand. So the user's goals would be to extend the hand using movement imagination. So the left and right bars that represents the brain activity over the hemispheres would increase. And if this is the left, in this case, the left hand imagination, this haptic robot would allow the users to perform the movement, right? This is right now an ongoing project that we have called N3RO. Following this type of endogenous signals, we have also providing several apps related to neurofeedback. Neurofeedback, we are considering a self-regulated activity, and in this case, this activity could be focused on specific frequencies and specific locations that usually they are related to different brain functions, for instance, attention, working memory, and so on, right? So with these apps, we can measure band power, we can measure also different cognitive measurements, and we can provide a simple and attractive visual feedbacks to motivate the subjects. And in fact, the motivation in this kind of apps is very important because it has been demonstrated that it affects a lot to the final performance. So here we are highlighting Ithaca, which is another app that we have on the app market. This Ithaca has 3 different scenarios. Here we have 2. For instance, the first one, this is the spaceship. We have only 1 degree of freedom to elevate the spaceship. And in this case, we have an implementation of SMR because you need to move the avatar to the right or to the left in order to collect the coins that are appearing in the scenario. Here we have another example of Eduardo using a neurofeedback application. In this case, it's very simple, only 1 degree of freedom. This is the third scenario. And we are measuring right now the alpha level on the parietal cortex, which is linked to the attention. So when the parameters are met, the cube elevates itself. And well, no presentation of MEDUSA would be enough if we don't demonstrate these functionalities in real time. So I will pass it over to Eduardo again to conduct a live demo of MEDUSA to illustrate of these functions.
Well, thank you, Victor, for the nice introduction of the platform. So what would we have to do if we wanted to install and to use MEDUSA? Actually, it's quite simple to install and to use. So I'm going to give an overview so you have a better idea of how this system works and how it can be used easily. Here, this is the main website, okay? So the first step, of course, would be to download the installer here from this button. And then we would have to execute the installer, okay? So we have to say that the installer is not signed, so you'll have to agree to disable the security measures of Microsoft. One important thing is that MEDUSA is only supported for Windows. So I think it's possible to use it in iOS and in Unix, in Linux, but you would have to use the source code, which is available also here in the GitHub button. This is a link that will lead you directly to the GitHub repository where all the source code of MEDUSA kernel, everything is there, and also the public apps. So this is the installer. It's really easy to install. You'll have to select the version that you want to install of MEDUSA. For example, you have here to choose an empty folder. Then you have to select a Python environment. So you have to install Python previously, and for these versions, the 2024 version, you will need Python 3.8, 3.9, or 3.10. So here you have to browse for this file, Python.exa, which is the main program of Python. You have to select this implementation of Python, and then you click install, and it will install all the components and all the necessary applications to work with MEDUSA. Well, this takes a while, so I'm going to skip this part, okay? And I'm going to move on with the presentation of the platform. So now I'm going to connect. Here we have a working neuroelectrics device, which is the Enovio EEG headset. So if we want to connect an Enovio headset to MEDUSA, we will have to start NIC2, which is the official program of neuroelectrics. Right now, I connected the device with Wi-Fi, so we have to click on use Wi-Fi, select the corresponding device, and just select use this device. Okay. Now the device is going to connect. Everything works because it's been on a while. Okay, now it's connected. We have a default protocol here saved for this demonstration. And here in the NIC, you have to configure your Enovio in the same way that you always do, but you have to make sure that this button is activated, the LSL server, because this is going this is what is going to stream the EEG data and the markers also to Medusa. So if this is enabled, you have to click on load protocol, and this will start streaming the EEG data. Now we have to go here to Medusa, and we have to look. Well, first of all, I'm going to this is what appears when you start. Medusa. Okay, so right now we have downloaded several apps that I'm going to show you right now. But the first thing to do is to connect your EEG device to Medusa so it can receive the EEG data here. So you have to click on this button here on the left and the upper left side. And here they will appear all the LSL streams that we are receiving at Medusa, including, of course, the Enovio EEG, that is the stream that we just started. Okay, so here you can configure different things. Normally, you don't have to change anything, but in this case, for this device, probably you need to change the name of the channels here, because they are streamed with standard names, channel 1, channel 2, channel 3. And for some applications, you will need to say the specific name of the channel in the 1020 standard. So for this kind of applications, if you don't put the channel names, they won't work, because we need the locations for the topographic blocks or other configurations. But in this case, this will be enough. So we click OK, everything is connected. And now we are receiving, or we are connected to this device. So the first step would be, in this case, to configure a new real-time plot panel, okay, and to add different charts here. The first and the basic one is the time plot multi-channel, because it allows to visualize all the channels at the same time, and it's the classical representation of the EEG. So I'm going to leave the default configuration, and right now, and here we can see the signal that we are receiving. What I'm going to do now is to add more plots, so we can see different real-time visualizations that are available in Medusa. For example, a power spectral density plot for one channel. Okay, there is also one for multiple channels, and also we can configure a topographic plot that is going to display the alpha power across the scalp in a real-time representation. So we click OK, and this is quite easy to configure, and you have a really complete representation of your input stream and in real time. So you can check things out, you can show the signal. This is really useful also for educational purposes. We use this at the university courses all the time to show how the EEG works and perform different experiments to see the artifacts in different representations. And afterwards, what you would need to do is to download an app. So this panel here is going to be empty, okay, at the beginning, and you have to come here to the app market on the website. Well, first of all, I'm going to uninstall the last app that we downloaded. Here we can download in the app market. For each app there is a brief explanation. Some of the apps have tutorials. Okay, most of them are quite simple because the apps are simple to use, but some of them are really complete and even with videos. So you can check this out if you have any doubt of how to use these apps. And you have to download the latest version. In this case, we downloaded version 2024 of Medusa, so we are using this. Sorry, I'm going to close this. And we are going to install the application that we just downloaded. By default is on the downloads folder. Okay, this is rec2. Well, it would be rec.app, but as we have different downloads, if you start Medusa for the first time, I wanted to show this. You have to log in, okay? So your user is linked to the different applications that we have. Sorry, it's difficult to... Okay. So this is the new platform that we just downloaded, was installing, and now it's open. Okay. So this process was occurring while I was explaining the other things. So we have to reconnect, of course, to the signal generator stream. Okay. Well, I'm not going to repeat all the steps. I'm only going to configure a time multiplot channel. Here we have the stream, and this would be the empty panel that we have. So here, if you want to install the application that we just downloaded, here you have to select the corresponding application. Okay, and if the user is the same, because each application comes with a license for an individual user, is going to be installed, and this is the recorder, but we can also download the rest of the applications. So I'm going to close right now this installation, because it would take a while to install all the apps that we want to show. Here the default folder is in C users, this thing. Okay, this is the installation that I was using before, where we have all the applications installed. And I'm going to show you the different applications that Victor was talking about before. So here we have the previous panel, which is already connected to the previous signal because it is still available. And here we can start the experiment. So to start experiment, you have to select the different apps. Okay, you have to select the app and press the app, the start app button. Okay. So in this panel, this will start the application. Here in this case, I have initiated the cursive block tapping test, which is one of the psychological tests that we have implemented. Well, in this case, we have the version, the default version in Spanish. Okay. So I'm going to close. This experiment, and I'm going to configure the language. So this is important too. You have to press this button here to configure the app, the run of this application, and I'm going to select the language English. Okay, so here you have all the options that the platform allows to configure, and we start the experiment. Okay. These apps are implemented in Unity, so it takes a little bit to start, but in the end, they're always open. Okay. So we have to press play here, and the experiment starts. Here we have the experiment that Victor talked about before. and this is the cursive blocking tapping test. Here, all the events that are occurring in the application are being recorded alongside with the EEG signal, all being synchronized at the same time. So even if you have different streams of or biosignals, you are going to have everything synchronized, and afterwards you can analyze all the data in a very straightforward manner. Okay, so I'm going to stop the run, and here when I stop the run, it appears the save recurrent file dialog. Okay, so here you can choose the path. By default is in the data folder that is within the installation folder of MEDUSA, and you can choose, of course, the file name. Okay, and you can choose between different formats, especially, and this is an interesting feature, you can save it in MATLAB format, so you can analyze it and load all the data in MATLAB directly if you want to use another toolbox different than MEDUSA kernel. Okay, if you want to analyze the signals with EEG or other signal or brainstorm, it's feasible. Okay, so this was the first step. Then we have, for example, this is the neurofeedback application. Okay, you have to select which channel are you going to train. You can read the documentation carefully if you want to know how this application works and what can you configure. But right now I'm going to launch the experiment, the application, and here we are going to see the main interface of the application. So here we have the first scenario, okay? And if I press play, well, in this case, nothing is going to happen. But if you are controlling the application with the EEG headset, you can start controlling the cue, and you can perform several repetitions and so on. And one of the other interesting applications is the code modulated visual evoked potentials that Victor showed before. Okay, here in this paradigm we can configure a lot of things, including, well, the run settings, the refresh rate of the screen, which is really important in this paradigm, the encodings. You can train models here, so you can record training examples or calibration examples with the application, and then you can train a model, specific model for the user, so you can start using the application. So this would be the life cycle of this BCI experiment. For example, you have to train a model before starting using the speller as we saw before when I wrote MEDUSA. So I think we'll leave it to the default configuration, and we can also start the application so you can quickly see how this application works. This is a very brief summary because we have a lot of functionalities, and especially in this version of the platform, we have introduced a few novelties, such as study management, so you don't have to save the file every single time after experiment. You can put it. You can just create a database and select the corresponding users, and you can save all the files there. And you can also configure sessions. Okay, this would be the paradigm here. Right now it's in the training phase, so if you train a model and load the model, you can start using the communication system through BCI. And I think this would be all for the live demonstration. I think we've covered the main points. Do you have something to add, Victor? Okay, so we are going to wrap up the presentation, and we can follow with the questions.
Perfect. Thank you, Victor and Eduardo, for this excellent presentation and real life demo. So we are open for questions right now. So if you want to ask any question, please use the Q&A tool. You will find the Q&A at the bottom of the Zoom application. And yeah, actually the first one, and probably everyone wants to ask, why MEDUSA? Why you call the platform and the application MEDUSA?
This is something that we hear a lot when we present the platform. Well, actually, it has sense because we were thinking about a creative name for the platform, and Victor here, I think it was his idea. We were thinking because we were using Python. We are measuring brain signals.
The thing is that, well, Python is a snake, right? And EEG is we are measuring brain activity, so brain plus snakes. So there is a mythological creature in the ancient Greek mythology that is related to that, which is Medusa, right? That she has snakes that come out from his head. So that's the reason we call it Medusa.
Perfect. Thank you. We have some questions already here that popped up during the presentation. The first one is from Ignacio. Actually, if MEDUSA could be used for hyperscanning in a setup where two subjects, or I guess more even, are doing the same experiment again at the same time, meaning connecting two different EEG devices stream to one single laptop, and I guess that when the laptop where MEDUSA is running.
Yeah, that's right. And actually, if you recall the presentation that Victor did earlier, we had a competitive game controlled by BCI. We can come back to the video so you can see. Here it is. So these two EEG devices are connected at the same time to the same computer. Okay, and the application in this case is analyzing both EEGs at the same time, one for each player, and each player controls its different turns of the game. No, so in this case, it can be used for competitive and collaborative BCIs, and I think this is really interesting because I don't think this is easy to implement in other platforms, and in MEDUSA is really easy.
Perfect. So actually you could use like an experiment in the classroom where you have many subjects. There is no limitation regarding number of devices.
No, there's not.
And have streams from every subject directly to MEDUSA, and then you synchronize all the signals.
That's right. Well, we always have the limitation of your computer, no, the power of your computer.
Yeah.
As we are processing and receiving more signals, more computer power you need. But that's the only limitation.
This will be actually for the online analysis, no? But just to collect and then analysis offline.
Yeah, just to collect, it's I don't think it's going to be a problem.
Okay, perfect. Thank you. Another question, Javier. Is there any application in MEDUSA app market developed for virtual reality glasses, for virtual reality applications?
Yeah. We don't have any virtual reality-based game in the app market right now, but we are working on it. Well, in the present, yes.
Okay. There is questions from anonymous attendee regarding Enobio devices. If those are natively compatible, I guess that yes, every device that will have LSL streaming will be directly compatible with your platform.
Yeah, that's right. But with neuroelectrics, it's pretty simple because you already have it implemented in your software, so it's pretty straightforward. With other hardware, it could be a little bit more challenging.
Okay, and there is a follow-up question actually. What about devices that are using single sensor like Muse, BrainLink, Emotive? If the users of these devices want to use neurofeedback platforms application you have on the MEDUSA app?
There are no limitations with this. You can connect a one single stream and the platform. If depends on the application. Maybe there are applications that need several channels. For example, if you're implementing a motor imagery paradigm, you will need at least 2 channels, one on each side of the cortex, no? But if the application is designed to work with one single channel, there is no limitation with that. I think it's important here to understand that each application is different. So the requirements for each application can vary. Okay, so there's no a straightforward answer. Some of the applications are going to work, some of them are not, but they are going to work if it makes sense to only use one channel. As in neurofeedback, in the neurofeedback app, it would be really simple.
Okay, so you could connect directly the devices that are very few channels, and they have a LSL stream. They will be directly compatible also with neurofeedback apps that you have on the platform. But this you have to somehow identify, checking the application, if there is a minimum number of channels that is required to run this application. By default, you can use only with one, I guess, no? Everyone, only that the effectiveness will be limited.
Yeah, of course. As long as you have an LS streaming, you can connect any headset. Let's say you have one channel or 16. It doesn't matter.
Right now, I can only think that this is a limitation on the motor imagery apps, because they require two channels, one of each side of the cortex. And when you are configuring the run, you have to select both sides of the cortex, which channels are you going to use. But this is the only case. I think in the rest of cases, you can use only one channel. This is not a problem. Of course,
Perfect.
if there is less channels, less accuracy, for example, in the spellers, but
you can always use. Yeah,
and
there is additional question: is Medusa only for research, or can be used for commercialized projects?
It can be used for commercialized projects too. Actually, we are trying to implement this in the platform, and we are open to collaborations with organizations that want to have a commercial application within Medusa just for their hardware. So this would be a very good sample of how it can be used for commercialization, to commercialize apps.
Okay, but I mean not by default. Only they will have to they will have to contact you and get your permission for commercialization. This is open, but based on some license, no?
Yeah, that's right.
Okay.
Right now it is. We are still working on it.
Perfect. And then additional question regarding collaboration initiative, like brand projects, neurotech startups, and similar.
Of course, we are open for collaboration. I mean, neurotech startups, also different research groups. We are open, and in fact, in the website we have a page just aimed at this purpose. Yeah, it's called Our Solutions. You can contact us there, so we can talk about this. Yeah.
Okay, and like more general question is, what do you think? What are the key barriers to spread the adoption of BCI in everyday life and professional settings, and then overall applications? Do you think that this is on the software level, on the hardware level, on the human level, on the adaptability of the techniques, on the signal level? What should be improved on all these sides? You think that this could be adapted to the real life in the very quick way?
Well, from my point of view, afterwards Victor can comment on that. I think it's a little bit of everything, no? We have to improve the hardware. We have to also focus on which applications BCI can be especially interesting and can give a little bit more of what is currently being doing. And also the human factor is important. It's difficult to put a headset and for example, right now it's very difficult to achieve good signal quality without gel. So the development of dry electrodes would be really, really interesting for this kind of applications, because actually what I think is that BCIs are going to develop as plug and play systems. So they have to be really easy to use and really easy to start working with them. This is not the case for neurorehabilitation applications. We are working also on that. Probably for these applications, what we need is to perform more experiments and perform wider clinical studies to demonstrate efficiency, and afterwards we can work on bringing this to the market.
Well, If we are talking about non-invasive BCIs, which are quite different to invasive BCIs, I think the most important thing to improve is the hardware. Well, that's the key points that Eduardo already said, but the hardware right now is quite dependent to the gel, and the signal quality can vary a lot. And also we have the problems of the synchronization of the different BCI paradigms. Right now there are a lack of paradigms that are currently asynchronous. I mean that most BCI paradigms are synchronous, so for instance, exogenous signals, the stimuli is constantly flashing, so you don't have a previous step to determine if the user wants to control the application or not. So we need to work a lot on that, on creating applications that has monitor attention before to switch the applications with other signals, then control it, then switch off back the application. So I think there's a lot of things that we can work on it, but mainly the hardware. Yes.
Perfect. Thank you. And my understanding is that your group actually is open to any collaboration from different researchers, not only researchers, even from the industry, and they can contact you and check. Actually, we can we can mention again medusabci.com. You can find all these applications and check and play. And actually, we have seen this LSL generator, EEG generator, that you don't even need the hardware to start playing and checking what you have on the web page, and actually get used to the application, and then at the end connect hardware and use the application. So this is the beautiful part of your solution.
Thank you very much. I wanted to, I think we already commented it through the application, but it's very important if people is interested in collaborations with us, and especially if we are talking about commercial collaborations. We have implemented in the app market, there are public or open source apps, and there are private apps that could be, for example, if we develop or a startup develops a new application for neurorehabilitation, they can upload to the app market their app, and they can commercialize via licensing, because they can give only license to specific users. So it would not be available for everyone there. So that's what I wanted to comment on that, because I think it can be an interesting option for collaboration.
Perfect. Thank you very much. We have a comment from Ardincia Esmondo. Thanks for the prompt answer. Cool stuff from Medusa. Looking for potential collaboration, and he didn't realize that was connected as anonymous. Okay, guys. So this was last question. Thank you very much. We'll be in touch regarding Medusa, regarding EEG. Thanks, Victor and Eduardo, for the presentation. Thank you for the questions. I don't know if you want to then mention all your group and everyone in the. I can see on the screen.
They wanted us to mention them. Of course, this is a collaborative work. It's not only Victor and me. A lot of people have participated, and here we have the main collaborators that we have currently at the lab, some of the PhD students that we have. Also Dr. Robert Tornero, which is the principal investigator of our group and has supervised all the development of this software. And we wanted to acknowledge also their work and their good work, actually.
Thank you very much. Thank you, everyone, for joining us today, and I hope you will join us again for the next webinars. You can visit our webpage, neuroelectrics.com, where you will find more information. So once again, thank you very much. Have a great day, and see you next time. Take care. Goodbye. Goodbye, everyone.
Bye-bye. Thank you. Bye-bye.